This use case focused on designing and simulating the first wall of a Tokamak fusion reactor, where capturing complex phenomena, such as heat flux deposition, photonic radiation, and heat transfer, with experimental level accuracy, poses a major computational challenge. Moreover, such complexity significantly increases computational demands and therefore costs too. At the Faculty of Mechanical Engineering, University of Ljubljana, LECAD laboratory focuses on the engineering design and development of advanced products for the most demanding operating conditions. It supports both industry and the scientific community by creating complex solutions and contributing to long-term societal challenges.
Solving this challenge required integrating and optimizing multiple simulations, thermal, magnetic, and optical. Limited resources weren't sufficient, so a scalable solution was essential to tackle the task effectively.
As a solution to this challenge, 3 codes have been connected in a scalable workflow to calculate a synthetic camera signal that represents a digital twin of a real infrared camera measurement. Optical simulations were performed, taking into account the temperature of the reactor wall and plasma power to mimic the movement of photons based on the radiation from the wall and plasma.
We simulate magnetic fields, trace particles, calculate heat transfer, and simulate radiation. Then we generate an image that's nearly identical to a real camera feed from inside the reactor.
The field line tracing code uses the full magnetic ripple field, including plasma contributions, to calculate heat loads on the wall. This is followed by solving heat transfer equations, and finally, optical simulation models the photonic radiation based on wall temperature and plasma power. Previously, this workflow ran on a single node, requiring manual data handling and offering limited scalability. Accelerat is transforming the workflow by integrating the HPC framework that enables the execution of all 3 simulation steps in parallel without the need for user intervention. The project is implementing automated data management systems and optimizing code for exascale computing, focusing on the parallel processing for field line tracing and thermal modeling.
Thanks to this approach, we now have the ability to process large datasets more efficiently, identify temperature hotspots, and ensure safety before damage occurs. This enhanced workflow is not only critical for accurate temperature detection, but also supports real-time monitoring in future reactor operations. Standardized data formats like HDF5 and NetCDF ensure interoperability and long-term usability of results.
By unifying field line tracing, thermal modeling, and optical simulation, LECAD's work through Accelerat reduces computational overhead, ensures simulation fidelity, and accelerates progress towards safe and efficient fusion energy. Key benefits this use case brings for research and industry are integrated monitoring across physical domains, automated, scalable workflow for complex reactors, accurate diagnostics despite optical distortion, and early detection of critical conditions.